Nice. So my name is Mike Young. I'm a data scientist at Uber. I was previously actually at Retina with these guys. So they're a great team. They do some fantastic work. I highly encourage you guys to do them after this. Is there any- All right, so today we're going to be talking about causal inference and estimating treatment effects using machine learning. It's a bunch of jargon, right? So before we start this, how many people here are data scientists? Okay, good half. How many people of you have sort of done work in causal inference? A couple? Okay, well, I'll just, quick disclaimer, I'm not an expert in causal inference. So if there is an expert in the crowd, feel free to just make meaningful discourse today. So anyway, with that said, let's go to the next slide. Before we dive into the actual deck, I found this cool graphic the other day. Everyone talks about correlation versus causation, right? We shouldn't get confused. But before we even answer that question, sometimes correlation is just by pure chance, right? In a similar way, the p-value happens. In fact, some people might have heard of, right? If you keep looking at your A/B test, at some point it's going to be stat sig. At some point, if you look at the world, you see some things that correlate. So if you think that the number of people who drowned by falling into a pool is correlated with the films that Nicolas Cage has appeared in, that's great, but that's the first word of caution. And then the next slide, this is probably what you're more familiar with, where ice cream sales and shark attacks they have a clear relationship. One clearly doesn't cause the other, right? There's a hidden confounding factor, which is the temperature. So it seems a little silly here, but oftentimes in business context, it's not common sense, right? So it's hard to tease out those hidden values. So with that, we'll talk about our agenda. So first, we'll talk about the fundamental problem in causal inference, AID, CAID, what those are, why do we care about CAID? We'll talk about propensity score models, propensity score matching, bunch of other stuff, and then at the end, causal ML. So my team at Uber and I just released a package a couple weeks ago called causal ML. So it will contain everything that we talked about today. Fork it, clone it, pip install it, do whatever you want. So what with that? So the fundamental problem in causal inference is that we want to know what the counterfactual is, just in general, right? Like, let's say in our universe we have a fictional character called Steve, and we show Steve a red button, right? We want to know if we could construct an alternate universe and copy Steve over, Control-C, Control-V, and show him a blue button, how that other version of Steve would react, right? In some KPI, clicks, revenue, whatever it is, right? The problem is that it's impossible, right? We can't just, in our world, we can't do that. So what do? We design a workaround, which is the gold standard for causal, in terms of estimating causal impact or causal lift, which is an A/B test, right? We find a bunch of people who are like Steve, and we aggregate that, and we show them the red button, and we find a bunch of other people who are like Steve. We say that's group B, essentially a randomized control experiment, right? So that's great, but the thing is, now we're comparing a bunch of people, right? It's aggregated, and that's fine if we want to know on average how well does the red button do compared to the blue button, but it doesn't help us answer that first question. And there's really no way that we'll ever be able to answer that in this world that we live in. But these newest techniques in causal inference allow us to sort of get closer to that unknown. And that's what we'll be talking about today. And another point is that, it's great if you have that set up in an A/B test, but what if you don't, right? What if the thing has passed, right? You've launched your product, or in some cases you just can't do an A/B test, right? In this example, let's say we have a website and we created a sidebar, right? And a product manager comes to you and says, okay, well, we didn't set up an A/B test. We want to know how did this sidebar do. So you go up and you go to SQL and you pull users who engage with the sidebar, and you say, how much did they contribute to your site? And then you go to the other side and you say, pull users who didn't engage with the sidebar, and how much they get. And you say, wow, there's a 4 times lift in revenue. The sidebar generated that, right? That's super dangerous, and a lot of people do that. And it seems obvious, but you'd be surprised. So the problem here is that the people that clicked it are like Steve. Let's just say they share the same characteristics, and the people that didn't click it are a mix of people. They're not just all unlike Steve, but there are a bunch of people who are like Steve and a bunch of people who are not like it, right? And so our job, in an ideal world, if we could figure out what this dotted line is, we could then separate them, segregate them, and then make that meaningful comparison, right? So we're already teasing out some ideas that we'll talk about. Okay, so before we dive into the propensity modeling, some definitions. 8 is just the average treatment effect. So it's just a fancy way of saying the lift at an aggregate level. It's a population level. So some quick math notation here. It's just the expected value of your outcome. So when we talk about y here, it's just going to be it could be like a regression or a classification, whatever it is, right? Let's just say for the purpose of today that we're predicting like a continuous outcome. Let's say it's revenue. So what's the expected revenue given that you're in a treatment group versus the expected revenue given you're in a control group? It's simple, right? The conditional average treatment effect has one more condition upon it, right? You can see the condition upon the treatment flag and X. So X is just your set of covariates, right? Everything you know about that user, your features, your demographics, your behavioral stuff. And so given that they're a treatment group and they are who they are, what is that expected difference, right? And so that gets at the user or segment level. And we're trying to solve that. So why do we care about Kate, right? Like at first you might say, okay, it's great that we know on average this button generates this lift. We can just multiply that by everyone to get the total expected amount. It turns out that, it's possible that the lift is different for everyone, right? And so in this case, we want to target those with the highest uplift, right? You can imagine that some people, on average, it generated 30% increase, but for some people, maybe it's 85%. For some people, it could have been 5%, and it could have been negative for others. So that's the second point. If for whatever reason, right, like typically speaking, you'll have a positive trend, but it is possible to generate a negative user level treatment effect. And then lastly, let's say you did your 8, right, your population level, and you got 0, stat sig, right? What if your distribution was just over that 0, right? It's centered at 0, but you have a bunch of people that had a positive impact, a bunch of people had negative. So what could you have done? You could have just shown whatever treatment it is you're giving them, whatever promotion that you're giving them, to the people that are in the positive, and just not shown them negative, because that wouldn't have negatively impacted your business, right? So let's move on. So we're back to that scenario earlier. Ignore the treatment control isn't the A/B test treatment control. It's just that when we talk about treatment, it means they're in the group of people that did something or that are labeled the treatment. So the procedure is pretty simple. So you build a propensity model, and a propensity model is simply a binary classification problem. And so outputs are a bunch of probabilities, right? So for every user in your treatment group, I'll stand here. For every user in your treatment group, you just kind of do a k-nearest neighbors, and you just keep matching them, and you find the most similar user to each person. And obviously, you want to add some threshold because you might have some like outlier person who's so spent so much money that you can't find someone similar, and that's fine. We'll just leave that person alone, and we won't find a match. And that's the threshold or caliper that you see there. So you just keep repeating step 2, with or without replacement. A bunch of considerations as it pertains to computation, but you just keep doing that until everyone has their match group, right? And so at the end of the day, hopefully, what we have is that we just have people who have similar characteristics. So if we go to the next slide, it's not really well labeled, but if you kind of squint, you can see that before the matching, this is the distribution of propensity scores or probabilities out of the propensity model. And by the way, the way to interpret what this propensity is what is the probability that the user was in the treatment group, right? And in the treatment group, in this case, was engaged with the sidebar, right? So we could interpret that as like, what was the probability before any of this happened that a user would engage with the sidebar to begin with, given their existing history? And then let's match all of them so that now, after we've matched it, so the distributions are aligned, the means are aligned, and now we can sort of be confident that we can compare these two groups. So one point to actually add, if you go back, is that you can extend this analysis exercise to any covariates you want, right? It's not just, let's say like, great, propensity is important, but I want to know recency, right? That's really important for me because I'm a business that's been around forever, or like just spending in the past 3 months. So I could actually add those to matching, or you could add several different distributions and match on those two to sort of hold those hidden confounders constant. So we're about to get a little bit into the technicalities here. I won't go too deep, but so far what we've done is that we've managed to match the propensities, the two groups, the treatment and control, so that they're sort of, we can compare them apples to apples now, right? But that's still at the aggregate level. So this, whatever's happening here, is going to help us figure out at the user level what this case is. So let's dive into just a few of them. Okay, so the S learner stands for single learner. So the procedure is that first you create a binary feature, whether it's like a treatment flag, whether the user is treatment or not. And then you train a single model with everyone. You throw everyone inside of it. And then what you do is that you set the treatment flag to 1 for everyone, and you have a bunch of predictions. So, and then you set the prediction flag to 0, and you have a bunch of predictions. All right. So now you have your y hat is treatment 0. Y hat, for people that are less familiar, just means our estimate of what y is, and y is our revenue. So what this final equation just means is like we have a single model, and we've simulated in the event that the treatment, everyone was a treatment user, and if everyone was a control user, and this is a vector, right? So this is actually the k-tis final vector of estimates. And the reason why they're called meta learners is that it's not super. I mean, so we are using. I should take a step back. The single model, you can throw anything at it, right? It's very model agnostic, which is very flexible, right? You can throw linear regression at it, you can throw neural net, whatever you want. It's still a supervised learning problem within the model, but the thing is, the final quantity that you're estimating is unknown. Like there's no like truth value to this, right? So you're actually using a supervised model to predict some outcomes, and then you're estimating that, and there's no error value. Right? You can calculate RMSE for this model, but at the end of the day, you don't know how good this is, right? So next slide. By the way, time check. How long do I have? Okay. So the T learner builds on the S learner. So here we build 2 models, right? So we only put the treatment users in the treatment model. We only put the control users in the control model. All right. And then what we do is that we take everyone and we throw them in the treatment model, we get a bunch of predictions. And we take everyone and we throw them in the control model, we get a bunch of predictions, and we just subtract it. Right? So it's a very similar idea, but the difference is that the first time we were only using 1 model with a binary treatment flag, and the second time we're actually just choosing 2 independent things. So, there are some nuances to why they would have output different results. This one, there's no exchange of information in between the 2, but so conceptually, hopefully that makes sense to people, right? At a high level, what we're doing is that we're like creating 2 different worlds, and we're just saying like, what if, and just subtracting that. Okay, so the X learner is probably the most complicated. I'm going to try to explain it, and if I sort of fall into this hole, we can talk about it afterwards. But you start by training the 2 models, like the T learners. But here's where it starts to diverge a bit. Instead of putting everyone in the treatment model and everyone in the control model, we take the control users and put them in the treatment model, and we take the treatment users and we put them in the control model. So you see how there's this X shape going? That's what I call the X learner. So why do we do that? The reason is that you want to take your control users and put them in the treatment world. Think about the models as just like worlds, right? Or like little games or scenarios, right? If you put the control people in the treatment world, what would they have done? If you put the control people in the treatment people in the control world, what would they have done? And you can subtract that with what they actually got, right? And so that's what this tau quantity is. We're taking the estimates with what they actually got. We're taking the estimates with what they actually got. And here it seems overkill, but we're going to build a model on top of that to predict what tau is. And you might be thinking like, well, why are you doing that? That's just silly. Ultimately, the goal is to establish a relationship between X, your covariates, your information about a user, which is like this here. Let's say we have a fresh batch of stuff that we only know what their X's are. and be able to know what their ultimate K is, which is down here. So if I had a bunch of people, which I don't know if they're treatment or control, actually they're about to go into an experiment, and I need to figure out should I make them a treatment or not. I don't have this information. If they were a treatment, then subtract that. So that's why I need to build a model around these two. Hopefully that makes some sense. And then to wrap it all up, it's just a weighted average where the weights are your propensity scores. So we're going back to like why do we care about K, right? We have a bunch of different meta learners in order to estimate this K quantity. Target those with highest uplift, right? That's what we talked about. So in the next slide, this is what an uplift curve could look like. So the way an uplift curve works is your x-axis for people that can't see is the population, and typically you'll rank them, right? You'll rank them from highest uplift to lowest uplift, and then this is just your gain. So this could be dollars, whatever it is. I've just normalized it to 1. But so what you do is that you take whatever learner. Each line is a different methodology. You take your learner and you rank everyone from the best all the way to the worst. So this gray line is random targeting. So if I targeted everyone randomly, for example, and I targeted the first 50 percentile of people, first half of people, I should expect to just get 50% of the gain, right? Does that make sense? So this would be 50% here. But if I did something more intelligent, and let's say the red line, which is the X learner, let's say this was like 10% or whatever it was, the first 10 percentile of your people can get you 50% of the gain. So that's pretty, if you go to the next slide, that's pretty powerful. So, just a few implications. You could offer promos to those customers because no matter what if they convert, they will lead to the highest uplift. And then just stop spamming these customers because, in this case, there is a negative, right? We've overshot that maximum uplift and they're actually giving you negative KPI, whatever that is. Yeah, we can go to the next slide. So to wrap this all up, again, I mentioned our team has put together this package. You can just go to GitHub/Uber/CausalML. It's actively being maintained. Another good package is actually, I think it's called PyLift by the guys at Wayfair. It's also really good. They use a slight, there's some crossover, but they do some things related to like causal trees or causal forests, which is actually tweaking the splitting criteria within a random forest in order to achieve causal inference, which is pretty interesting. But yeah, this is my actually wait, sorry. I have one final slide. Go to the next one. So this is a bit of a shameless plug. So some of you may have heard me sort of talk about this, but I'm also launching a program. It's sort of a part-time, 12 weeks accelerated program in machine learning and data science, basically to help folks out. So once upon a time, I didn't know how to code. I didn't study CS undergrad or stats or anything. I took a couple stacks class, but there's a bunch of bootcamp routes. There's Coursera reviews. There's a lot of different things, and there's just so much stuff in the world. And I managed to make that transition fairly quickly, and so which is why the word accelerator is there. I want to be able to create a way for other people to also follow that sort of chart that I've made. And so basically, it's a 12-week program. It's part-time on evenings, and you guys can check out the website. Or if you just want to chat about anything, I always want to sort of connect with people and teach stuff. So that's everything. Question?
So my question was on the X-learner. When you were talking about creating the two simulated worlds and then having the populations sort of cross over for testing, because you already fit for likeness in the beginning, is this sort of a secondary or second layer of tests so that you can start to see the differences between those covariates? Is that kind of?
Yeah, so when you're fitting for likeness, I should actually, can you go to the 2 slides from here? One more. Oh, sorry, forward. One slide after the plug.
One slide after the plug.
Yeah. So you can kind of think about your data as like there's a pre-treatment period, there's like a treatment period, and there's a post-treatment period. So like here is where, and this is time, right? Here's where we're like
observing users to see if they did stuff. And in this case, like this cart is what we're interested in. So what we're controlling for is this stuff here, the pre-treatment. And what we're estimating, the y, is here. So even though you've controlled for all this, this still could be very much different. And so that's why that's why any of the learners work, is because we're only controlling for the pre-treatment stuff. We're trying to understand the y and the post. Say it.
So you for FBS just for the treatment period, and you don't include the treatment period.
As part of the covariance?
Yeah.
Yeah. So you can include some of the stuff during the treatment period. It depends on your problem. So the reason why it's an ambiguous answer is that, let's say you are deciding to, you're creating a model to decide whether to show a certain treatment to someone, right? If you're taking features and attributes from the treatment period, when you're actually deploying that model or deploying this sort of strategy as to whether I want to serve someone, you're not going to be in that treatment period yet. You're still going to be in that pre-treatment period. So like at time of scoring, you're going to be here. So that's why you typically don't include that. However, if all you're curious about is just understanding that user level treatment effect and you don't care about deploying it afterwards, then yes, you can include features here. Hopefully that distinction is clear. Yeah, good question. So
Can you
the
repeat the
difference.
question?
Oh, sorry. The question was, how is this different from a difference in difference approach? So the difference in difference approach is after we do the sort of matching, we just take a difference. Instead of taking the difference in the post, we'll take the difference between the pre versus the post and the pre versus the post. That's correct, right? So you can do that, and that's another way to validate your methodology here. So what a meta learner allows you to do is to build a model to generalize the trend, right? So you could have a new user who has nothing to do with this treatment group but has the same X, and you can feed it in, and it would output what that expected output. With a diff and diff model, you would only have scalar outputs for the existing net. Question on the back?
That's also probably why you wouldn't use like permutation tests to calculate like a or a right? Because
Permutation test?
yeah, so like basically you have your treatment group and control group and you're calculating what the treatment effect was for each.
Yeah.
And then you basically permutate the entire population.
Yeah.
Compare these.
Oh,
to see
interesting.
if you have stats between that. But then I think that doesn't give you.
That's very interesting. So you permute the treatment flag.
Yeah, so you permute the treatment flag, so you
Yeah.
essentially create like
Yeah.
a random
Yeah.
population.
Almost like a set. Yeah. Yeah.
But I don't think it gives you the most treatment effect.
No, what it would give you is whether there's a statistic
Yeah.
difference, right?
That's very
Yeah. So I guess that's a good like sanity check, right? But if this model is spitting out like 80% increase, and then a permutation test said there's no difference, then you should be worried about what's going on here. Yeah.
Just one more. If there's one more, you go one more.
Final questions? No. All right, thanks, guys.
Thank you, Mike, so much for talking about causal inference. It's very interesting, although I do have to disagree, regardless of all the explanations you tell me, I still think ice cream sales make shark attacks happen. It's personal belief. Thank you so much again. So that was our first speaker. We have a second speaker. I'd love to invite her up now. Please welcome Irina to the stage.